All right, I'm going to do another example using the p-value method. All right, this test is a nutritionist believes that 12-ounce boxes of cereal should contain an average of 1.2 ounces of bran. She suspects that a popular cereal has a different mean bran content. She carefully analyzes the content of a random sample of 20 12-ounce boxes of the cereal and finds that the mean bran content is 1.16 ounces. It is known that the standard deviation of the bran content of all such boxes of cereal is 0.08 and that the content is normally distributed. All right, so let's break down the things that we know there. All right, so we want to try to test if the average of 1.2 ounces of bran. This is our given essentially as to what we're testing against. So our sample finds the mean bran content as 1.16. So that means X bar equals 1.16. We're also given that we have 20 boxes, so that's N, so N equals 20. And we also know that the standard deviation is 0.08. Standard deviation of all, so we don't have the sample, we have the population, sigma, that's 0.08. We're also given this other piece of information that they're normally distributed. That's actually, in this case, something that we need because we have a small sample here. We have N is just 20, but we're dealing with a mean. So here we're testing, let's say, do the data provide sufficient evidence to conclude that the mean bran content of all 12-ounce boxes of this cereal differs from 1.2 ounces, and use 0.05 level of significance. That's our alpha there. So we've got really three options as to what we would be doing for a test hypothesis: a greater than situation, a less than situation, or it doesn't equal. Well, it differs means it's a problem if it's too much above or too much below. So first, let's write down our null and alternative hypothesis. Our null, HO, is that the mean equals 1.2. And we can put ounces. Our alternative, HA, is that the mean differs, so it doesn't equal 1.2 ounces. That's okay. Again, we know we are dealing with a mean. And N equals 20. It's not greater than or equal to 30, so we have a small sample. Now, we also have the piece of information that data is normally distributed. So we can use the T. Use the T distribution. All right, so we want to run the t-test. In our calculator, we're going to type in stat, then go to tests, and then go to t-test. All of these tests or intervals are well named. If they say the word test, it's a test hypothesis of some sort. If it says the word interval or the partial word int, which means interval, it's an interval. So here we want test. So let's go. Stat, turn it on. Stat tests. The t-test is the option, number 2. We do have stats. Mu sub 0, again, that's our target value, and that's going to be 1.2. X bar is given as 1.16. S, we don't have S, but we do have sigma, that's 0.08. And finally, N is 20. So which option here? Again, this option is very important for the calculation of the p-value. We're not going to do it, but the calculator needs to be able to know which sort of test we're running. In this case, it's a two-tailed test, and doesn't equal is our option here. So we're going to choose doesn't equal by hitting enter there. And that's all we need. Now we can go to calculate. We have the test statistic t, but more importantly, we have this p-value. It's 0.0375. So p-value, 0.0375. We need to compare that to alpha. Well, it's less than alpha, or less than or equal to alpha specifically. And because of that, we fail, we reject. The null hypothesis HO in favor of the alternative. And if you look here, that t-value, that negative 2.2, almost 24, our z-value for the critical value for that would be 1.96 when we break up 0.05 to 0.025. We know that the t distribution does it a little differently, but still it's clearly large enough, or it's far enough away, certainly on the left-hand side, to be above that negative critical value of the left. So here we know we're going to reject HO. If we did it as test in this manner, our negative t of alpha over 2 would be right here, whatever that number would be, and our critical value is right about here. That is the t-test. And our p-value is that area multiplied by 2, because actually we have a positive t of alpha over 2 over here. So we have two different ranges it can be in. We know it's the one on the left from what our t-value is at negative 2.24. So this is, again, a way to deal with a p-value, a little easier way to do the tests.